Hi everyone, I'm Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today's topic is tunnel diode. So let us see the overview of today's presentation. So let us start with the introduction to the tunnel diode and the construction of tunnel diode and operation or working principle of tunnel diode, then followed by its characteristics and conclude with the summary. So, tunnel diodes. Tunnel diodes exploit a strange quantum phenomenon called a resonant tunneling to provide negative resistance forward bias characteristics. So, this is named typical word negative resistance forward bias characteristics. So, this is the typical special purpose diode which is used in many applications. The tunnel diode is also known as Esaki diode. So, a Japanese scientist. So, it was invented by Leo Esaki in 1957, and for this invention, so he received a Nobel Prize in 1973. So, they were longer lived than traveling wave tube amplifiers. In olden days, traveling wave tubes are used to amplify a signal. So, however, this traveling wave tubes required more space, so and gain also, of course, gain is more compared to other components. So traveling wave tubes require more space, so that is the biggest problem, and noise also more. So an important consideration in satellite transmitters. Okay, so they were, but the tunnel diodes were very longer lived than traveling wave tubes because the maintenance is very less and they are compact. So that is why, so they are longer lived than traveling wave tubes. Tunnel diodes are also resistant to radiation because of the heavy doping. So tunnel diodes are heavily doped devices. So they also resistant to radiation. So because they are heavily doped, they can sustain for high radiations also. So even small signal tunnel diodes are expensive and difficult to find today. So the drawback with the tunnel diodes are they are very cost effective. So they are very costly, and even small signal tunnel diodes are expensive and difficult to find today. So that's why that is the drawback of tunnel diode. So there is one remaining manufacturer of germanium tunnel diodes and none for silicon devices. So only tunnel diodes can be manufactured using germanium tunnel diodes and none for the silicon devices. So they are sometimes used in military equipment because they are insensitive to radiation and large temperature changes. So usually there is any environmental changes, let us say temperature in summer, sunny day. So due to high temperature, there is a change in the properties of semiconducting materials. So, but coming to the tunnel diodes have they are very insensitive, less sensitive to radiation and large temperature changes. So they can the properties of tunnel diodes may not change even drastic environmental changes. So there has been some research involving in the possible integration of silicon tunnel diodes into CMOS integrated circuits. This is the advanced research which are going to integrate silicon tunnel diodes into the CMOS integrated circuits. So CMOS integrated means complementary metal oxide semiconductor integrated chips. So that means it will become very compact and robust. So that is the advantage with this integration chips. So they are thought to be capable of switching 100 gigahertz digital circuits. So 100 gigahertz means very high frequency. So as frequency increases, obviously the size of the particular material becomes very compact. So that becomes that leads to robustness or uh, they can sustain for environmental changes. So that is the introduction to the tunnel diodes. So what is tunnel diode? So this is a symbol for tunnel diode. So it is similar to normal PN junction diode. So this is your normal PN junction diode, anode, cathode. So here just T, tunnel. Tunnel means actually this is about so there is a relation between two barriers. So that we can represent like this tunnel diode. So anode P-type material and cathode terminal. Okay. So a tunnel diode is a very heavily doped PN junction diode. In a tunnel diode, electric current decreases as the applied voltage increases. So that is negative resistance. At high voltage, it works as an ordinary PN junction diode. At high voltages, it works as an ordinary PN junction diode. So the electric current decreases as the applied voltage increases. See here, electric current decreases when as the applied voltage increases. So usually according to Ohm's law, what we have, V is equal to IR, correct? So voltage increases, current also increases. So in contrast, in a tunnel diode, electric current decreases as the applied voltage increases. So that represents the negative resistance characteristics of a tunnel diode. At high voltage, it works as an ordinary PN junction diode. In tunnel diode, electric current is due to tunneling effect. Okay. So due to its fast switching ability, it is used to high frequency oscillators and amplifiers. So these are the applications of tunnel diode, because it has a peculiar property that it has fast switching capability. So hence they are used in high frequency oscillators and amplifiers. High frequency oscillators can be used in RF circuits like that. And due to the tunneling effect, charge carriers move across depletion layer at a very low voltage. So due to tunneling effect, so it requires very less voltage. So for at very low voltage also, the charge carriers moves across the depletion layer, even at low, because it is heavily doped. So many number of charge carriers available, and then due to tunneling effect, charge carriers can easily move or cross the junction. The circuit shown below is the symbol diagram of the tunnel diode. This one is the tunnel diode symbol. And in tunnel diode, the P terminal acts as an anode and the N terminal acts as a cathode. This just normal PN junction diode. Working of a tunnel diode. How tunnel diode works? So see here, this is a anode and this is cathode. Anode is positive, cathode is negative here. So here this represents positively charged hole, and then electron negatively charged. So this is the depletion region. So because your tunnel diode is heavily doped, so there is the thin layer, depletion layer will be present. So width of the depletion region depends on the level of doping in semiconductor material. So if the doping is more, so the depletion region, so usually very thin. So if the doping level is high, then the width of the depletion region is thin. And if the doping level is low, then the width of the depletion layer is more. So depending upon the doping concentration, the width change. So if doping is increased, the depletion width will be reduced, very thin. So the depletion layer or depletion width is thin in case of heavily doped materials. In tunnel diode, width of the depletion region is very thin because tunnel diode is very highly doped semiconductor material. Thus, when low voltage is applied across the terminal in forward biasing, electron moves across the depletion from N-type semiconductor towards P-type semiconductor. So, because it is heavily doped, the depletion region is very thin, and hence there is a chance of the movement of electrons from N region to P region. So therefore, forward biasing, see here, when low voltage is applied across the terminal in forward biasing, electron moves across the depletion from N-type semiconducting towards the P-type semiconducting. So they move like this. So if the depletion width is more, so we have to excite to move, because there is no chance if the no chance for the charge carriers to move P to N or N to P. So in such case we have to excite externally. So we have to bias the diode. So now in unbiased condition or unbiased tunnel diode, so what happens? In unbiased tunnel diode, so there is no current flow. There is no current flow here. The width of the depletion region depends on the level of doping in semiconductors. Just we have discussed. Because of overlapping of electron of the conduction band of N type and the whole of the valency band of the P type are nearly at same level. So if you see, this is P region. In that P region we have conduction band, valency band, and here also N region, conduction band and valency band. So they are at same level. So therefore, because of overlapping of electron of the conduction band of N type and whole of the valency band of P type are nearly at the same level. So balance. So there is no movement of charge carriers. So both are at same level. So there is no movement of charge particles carriers. So therefore there is no current conduction. So thus when temperature increases, some electron tunnel from the conduction band of N type to the valency band of P type, some hole tunnels from the valency band P type to conduction band N type semiconductor materials. So whenever temperature changes, so these charge carriers acquire some energy and they may move from one side to another side, that is P to N, N to P. So when temperature increases, some electron tunnel from conduction band. So this is your conduction band to the conduction band of N type to the valency band of the P type. So valency band, because valency band empty, so valency band of the P type. So conduction band from the N type will move to the valency band of the P side like this. So in such case what happens? Some hole tunnels from the valency band to valency band from P type to conduction band of the N type. So thus vice versa. So they change the movement of charge particles. So but the current flow is zero because the number of tunnel electrons and holes are the same but in opposite direction. So that's why if you see the VI characteristics, there is no current flow. This is unbiased tunnel diode. So in forward bias condition, that means we have to apply some positive voltage applied across the tunnel diode. What happens? When a small positive voltage is applied less than the potential of the depletion region. So this is important. So we have to apply the small positive voltage which is less than the potential of the depletion region. So here if you see this PN diode, tunnel diode, anode, cathode. So there is some potential barrier voltage VB, and so the applied voltage, whatever the forward voltage applied we have, so this must be less than the potential of the depletion region. So that is which is in contrast to the normal PN junction diode. So some of the electrons of the conduction band of the N type tunnel in the empty valency band of the P type. So some of the electrons, so these are the electrons, so they move towards the P side. So the electrons from the conduction band of N side will move to the valency band of the P side. So they move, there is a chance of recombination. So this creates a small current flow through the diode. So that starts some current flow initially. So this is the VI characteristics when forward bias is applied to across the tunnel diode. Next, at VP. So voltage is increased further. So the peak voltage. So if you increase the voltage further, then when voltage is increased, a large number of free electrons at the N side and holes at the P side generates. So what happens now? So here large number of move towards this into the N2P region, and hence because of the increase in the voltage, overlapping is increased. So here overlapping is increased due to the increase in the voltage. The energy level of the conduction band of N-type is exactly equal to the energy level of valency band at P-type, resulting maximum tunnel current flow. So maximum tunnel happens here. So when we increase further, so and they reach some saturation value. So that current is called peak current IP, and that voltage is called peak voltage VP, right? So maximum tunneling happens here. So if the applied voltage is more than peak voltage, so when the peak voltage and the tunnel applying voltage is greater than the peak voltage, what happens? The energy level of the conduction band at the N side and the valency band of the P side misalign. So here what happens? So there is a misalignment of the charge particles on P side and N side. Due to this misalignment, tunneling of the charge carrier decreases. The tunneling of the charge carriers decreases, as a result decrease in the tunnel current. So up to this VP, so there is a linear relation between voltage and current. Okay, so linearly increases initially. So after that peak voltage, if you further increase the input voltage greater than peak voltage, then so misalignment takes place. So due to that, the current, tunneling current decreases slowly. So that is like this. So there are three regions we can observe from the characteristics of tunnel diode. The portion of the curve in which current increases linearly is known as ohmic region. So this is your ohmic region, right? And then ohmic region, the tunnel diode behaves like a linear normal diode, because as voltage increases, current also increases. So it's look like a normal VI characteristics of normal PN junction diode. Negative resistance region, portion of the curve in which tunnel current decreases known as negative resistance region. So this part is negative resistance. What happens here? When voltage increases, current is decreasing here. When voltage increases, current is decreasing. So that means negative resistance region. And then saturation region. At a very high voltage, diode attains saturation level. In the saturation region, tunnel diode behaves like a forward biased ordinary diode in which current increases exponentially. So in this region, so after reaching some value point, after that again it reaches some, after that saturation level, if you further increase, the diode acts as a normal PN junction diode. So it has linearly, the current increases linearly with the increase in the voltage. So these are characteristics of tunnel diode. Let us conclude today's session. So what we have learned today, so we have learned introduction to the tunnel diode, the construction and operation of tunnel diode. So tunnel diodes are heavily doped semiconducting materials. So due to that, and it has very peculiar property that it shows negative resistance region. That means when we increase the input voltage, there is a decrease in the current. So actually, when we increase the input voltage, correspondingly current also increases. This is in case of normal PN junction diode. So whereas in this case, in tunnel diodes, they are specially designed devices. So they are specially designed because it is heavily doped. Tunnel diode is heavily doped. So as we increase the input voltage compared to the other normal PN junction diodes, the current decreases. So this is the basic nature of tunnel diode. Now, and we have seen the characteristics of tunnel diode, and now probably next topic will be application of tunnel diode. So where we can utilize this concept of tunneling effect for specific application. Thank you.